Oh, it's a long story, and I came here in 2009, and I actually started with something else. Um, I was involved in some work related to gas chromatograph, which is instrument that measures volatile organic compounds in the atmosphere. But then that project will not get funded. So I, at that time, I think it's in 2010, I actually didn't have a project for my doctoral study. So I think that's a pretty common problem for like especially graduate student and doctor student, and they prepare for something and that's not get funded. So then the projects were looking for someone can pick up the work for them because they had very long time periods of measurement data, and they want someone to study those data, study like science questions based on the long-term observation, and they want somebody to do like modeling work, and most importantly, they have fundings for me. So I think, okay, it's not initial interest for me, but I think I can try it. So I started work on Pico Project in 2010, and I started to learn. Um, I didn't have much background, modeling background, um, so I started to learn those computer tools, computer languages, IDEA program, stuff like that. Um, so I think this is also interesting to me. It's different from measurement. It's more about modeling work, um, and I feels I have more control about the model stuff, like process, atmospheric, physical, and chemical process. Have more control of it. I mean, it's not real, but it's in a computer. It's a calculation process. Um, and I don't have to deal with like instrument problem because sometimes there's tricky problem with detectors, instruments. So I think I can work on this for my doctor study. So I said yes when they offered me another year's funding. So that's how I get.
And we decided to accept this challenge of trying to find a way to keep scientific activity that we felt um, would honor Richard Honrath's memory and also be very scientifically interesting for us. And so we, after much conversation with various people, decided to propose some very fundamental questions about characterizing aerosol, which are the suspended particles in the air. And we were initially really interested in aerosol properties, particularly after long-range transport, because it's so rare to be able to have access to intercept those particles after they've traveled for thousands of kilometers. And so there's so much work that can be done as far as understanding, what is the chemical composition of them, what do they look like, what source regions do they come from, how much secondary processing has occurred. So many questions, and these are really important because of the global scale models that are being used to extrapolate properties that then feed into climate models. And so in order to improve the chemistry models, the basic atmospheric chemistry and the radiation models and various things, we need to have better measurements, especially for remote atmospheres, things that can be extrapolated over a larger spatial area. Would you like to add to that?
No, I think that's good. Maybe the only thing is that when we met to come up with new question, scientific question, the idea was not only the practical thing of keeping the station going, of course, but really to make something that Richard himself would be proud of him to really do some good science with it.
Yeah, I 100% agree with that. It's kind of interesting because, you know, Richard had started this atmospheric science program at Michigan Tech, and he established the station, and then he was part of the hiring committee that hired both of us here, and so we definitely have a lot of admiration for him, and we're very, yeah, we're very grateful for his contributions.
I got involved in Pico Project by becoming a postdoctoral researcher with Professor Lynn Mazzoleni. She asked me if I would be a postdoc with her, and I extremely joyfully accepted that position. So that's how I came on the board with the project.
I guess it was, to some degree, kind of just worked out by accident. I started in the physics department here, and kind of found out about this atmospheric physics program after I had already decided to go to grad school here. And then I started working with Claudio, and I really kind of got interested in working with lasers. And also I heard about this really cool project that he works on, which takes him to an island in the middle of the Atlantic Ocean. And so I started working with him, though, I mean, more so with my interest in some of the physics that goes on with the lasers, and a little bit of funding ended up opening up with the Pico Project, so I got to get involved in that, so.
When I started, actually, they need some people to process the data because there were a lot of instruments at Pico, and you probably saw those instruments, and there's like calibration process for the instrument, and sometimes the instrument experience a shutdown period, so they need somebody to process the raw data, and then those data can be used in the following modeling work. So I start to learn those process at first. I work a little bit on the NOx, we call it calibration, data calibration, data process, just to improve verify those data, like quality control stuff. So then I start to learn flex part modeling, which is long-range dispersion model. So it sounds very complicated, but it basically tracks air masses in the atmosphere. So if you have like air particle here at Houghton, so the model will calculate like after 10 days where is the particle in the atmosphere. So probably it's over the North Atlantic, probably it's in Europe. So that's how this modeling works. People in the Pico project want to know this because they have a lot of measurement. They want to know where the air came from and what happened during the transport. So I use these modeling tools to provide, we call it transport trajectories. So transport trajectories from North America to the station, to the Pico station. And I also do like chemical evolution, so how the pollution get transformed, changed during the transport. So that I think that's related to part related to the climate change for North Atlantic or the global atmosphere. And another part we just started recently is measurement of radionuclides. People collected filter samples at Pico, and most of those are aerosol samples. and I extract the radionuclides material from the aerosol samples. The reason we do this is the radionuclides materials have specific sources. So some of those come from the space, and some of those come from continental sources. So by looking at that, we can tell where the aerosol come from, and also we, radionuclide materials have activities. So by measuring the activity of radionuclides, we can calculate how long it stayed in atmosphere after emitted from specific sources. So I think that's the part we start recently in this summer, late last summer, mostly this summer. It's like the Pico is in the middle of North Atlantic Ocean, and there will be transport from North America mainly because that's at middle altitude region. So there's westerly winds at that region, and sometimes we can get some aerosol transport from Europe also, and also some dust samples from Africa. So it depends how the circulation system of the atmosphere. So, but for most of the time, we observe transport from North America.
My role specifically with Lynn is the analysis of organic aerosols with ultra-high resolution, mass spectrometry, and a bit more widely. We have 4 high-volume samplers at the Pico Mountain that we brought up and installed. They were actually brought up by mountain guides of the Pico Mountain. And there we do the measurements of aerosols, which are collected during 24 hours on the filters. And then we take those filters back to the lab and analyze them for various, for the whole array, ideally, of compositional characteristics. So what we do, and what is really exciting for me with working with Lynn, is the capability to get the molecular level details of the chemical composition of the aerosols we are collecting. Because various research has shown that on the molecular level, chemical species will be influencing differently things such as capability to be cloud condensation nuclei, capability to influence our health, and yeah, in a big picture to change our climate.
So we're looking at more of the optical properties of these particles. So, we're all kind of looking at these little particles that are floating through the air, and we're looking at, well, what do they do when the light hits them? Do they absorb the light? Do they heat up when that happens? Do they reflect the light? Do they scatter the light in a lot of different directions? And we look at, how is that going to affect the rest of the atmosphere? And we look at the morphology of the particle, which is like the way that the particle is shaped. Is it like a sphere, or is it like a long chain of little particles put together? Or sometimes they even come out looking kind of more like a cube. And we look at how those things plan, and then of course also their chemistry will affect, what's actually in the particle will affect how it interacts with light.
This is a very large project, and I don't want to even hint that that this is my merit or Richard's merit. This is the merit of many, many people that are involved in this project. Claudio and I, we get to lead the project, and we get to be responsible for the budget and to the federal agencies. But we wouldn't be able to do this work without collaboration Particularly Professor Paulo Fajalo of the University of the Azores is a key collaborator. And then of course we have a few additional co-PIs, including Detlev Helmick from the University of Colorado, Seth Olson from the University of Illinois. They both have very major parts of the project that they're contributing to. So Detlev is more or less in charge of most of the trace gas measurements. He brings a lot of senior expertise to the project, whereas he was collaborating with Richard for a few years prior. And Seth Olson is a modeler, and he works on both regional and global scale chemistry models. And those models can also give information about radiative transfer and energy in the atmosphere. And then we hired a couple of postdoctoral researchers, Katya Zampina, Sumit Kumar. Both of them have been involved in the project in very substantial ways. And then several students have been working on this as well. So Bo Zhang, Kendra Wright, Swaroop Chima. And then we have a few technicians who help with a lot of the nuts and bolts activity, including Mike Joback and Jacques Huber. And then additional senior persons who oversee specific aspects of the data analysis, contributions and modeling. So for example, Chris Owen, who has a long history of work at the station, and he's an expert in transport modeling. He is co-advising one of the students on the project. Professor Louisa Kramer, she's an expert in trace gases and also satellite retrievals of gases. Professor Noel Urban is overseeing some of the chemical measurements, and also Professor Judith Perlinger also oversees some of the chemical measurements and some of the modeling of that. And then we're especially fortunate this year to have Valentina Harkness involved in the project to develop some of this outreach and to help us, let's say, downscale some of our technical words and make them a little bit more friendly to a broader audience. And so we really appreciate her collaboration.
So for the research part, so this is very comprehensive project. People study a lot of stuff at station. Every people has his or her expertise. Like me, when I do modeling work, I need, for the perspective of the research, I need data, measurement data, to put into my model. So, but I'm not an expert for the measurement part. So I think they send people to the station and work with the instrument and collect the data, send those data to me. And they also provide, they also do some data processing work so that data can be used in my model. For how to do the research, I'm a doctoral student, and there are a lot of professors in this group, and during my work they actually give a lot of suggestions, like how this is the specific point you want to look into, and how to prepare publication or presentation, stuff like that. So I'm happy that we have such a big group that we can talk with people with different expertise, different experience.
I would say in science it means everything. So generally in science, I think working in a team means everything. We can do so little by ourselves, and we can do so much talking and working with other people. There is no growth without other people, and without other people around you. They push you, they make you a better human, they make you a better scientist. They ask you questions you don't know answers to, so you hopefully want to think about them and answer them eventually, or just keep them at the back burner. So I think generally in science there is no growth if we are just working by ourselves.
We gain a lot, but especially the project gains quite a bit because the expertise of all of the individuals is so unique. And even for students who they haven't necessarily developed their expertise yet, they bring a unique perspective to the project, which is really important. And we wouldn't be able to do not even a small fraction of what we're doing right now if we didn't have the team of collaborators.
You know, my background is physics, and now I'm a physics graduate student. So at this point, I have like very basic introductory chemistry. You know, I just have a really rough understanding. So this is like a very specific thing that by working with chemists in the group, we get a much better picture of what's going on. I mean, we're not chemists. We don't understand these interactions that are taking place in the air. We don't necessarily understand the things that, you know, maybe would have happened before the particles got there, or perhaps what would happen after the particles got there. So we get to work with these groups and learn more about the particles. And also just it makes it interesting and I think enriching that we do work with people who are from all over the world, and I think that offers just a unique perspective, and just working with people from different backgrounds and who have a different scientific background but also different cultural backgrounds, I think really makes the entire project more enriching and more interesting.
Let's say, from my point of view, collaboration can be sharing, basically, and working ideas together with some propose, some aim, some target that we can join efforts to attain the same objective from different point of views. If I really understand your question, because I'm not really sure I really pick it up correctly.
Yeah, but is collaboration easy?
Let's say collaboration depends a lot on the people, you know, and sometimes it's easy, sometimes it's difficult, and I don't know, I don't feel very difficult to collaborate with people, and I like to collaborate and share, and I've been lucky in a general sense to work with all these people in this project. For me, I think it's great.
Collaboration means everything, really, and in the case of the Pico Mountain, it's very alive because you really cannot do it without the help of your buddies. Call them buddies, call them collaborators, call them people you work with or run the station with, but we are very dependent on each other, and it's awesome.